we were going to write the monad instances for the combinations of the above transformers with an arbitrary monad. So I think we started with maybe T. That was the first one we did. And essentially we just implemented the instances for it. And then there's a bunch of other ones. So we'll just implement those real quick. And then these pure applications. So it says start with the implementation of return and bind for the monad and replace pure applications and bindings with do notation. I don't think we'll do that. I mean, like we can do that by just doing you know, putting a do here, but I don't see why we would do that particular case. Anyway, I need to shut the door real quick. Give me 1 second. Shoulder. All right, so let's just do, I feel like we just implemented reader T recently and also state T and writer and the continuation. I don't really want to do all of these. I've done them like what feels like 1,000,000 times now. I suppose we could implement cont T one more time because that one's always a bit tricky for me. But I kind of want to just keep going. I think that's what I'm going to do. I feel pretty confident of my ability to implement these cases now. So I would like to learn more about how to use the transformers stacked together. That's sort of what I'm more interested in. So let's keep going. It says there's an important monad missing from table transformers, the list monad. The problem is that the naive implementation only works correctly if M is a commutative monad for the reasons we talked about previously. Here is the monad instance for list T. %. All right, so apparently there's okay, so it says well, let me just bring it up. I can bring it up real quick. It wouldn't be that hard. I need to find list T. We'll look in here for the add instance. Oh, wrong one. Okay, so I think the key here is that at each step, like the naive implementation of this does not have a monadic step in each loop, or not loop, that's not the correct way to say this, for each A and B, I guess. So it's really important that this step here, I guess, happens in sequence. So you need to use the monad case. Otherwise, you get incorrect properties. So we did test that, I think, when we did chapter 10. So we looked at an example where this fails. So you need to have this monadic operation here for this to work correctly. Apparently, you can also implement list T with there's a package called list transformer that has a slightly different transform. Is it just this one? This packet, I don't know if this is the right one. Let's see. Source. No, I think this one's different. But this is kind of interesting. It has like this additional maybe in here. What's the definition of this? I don't know what this is for. Streaming of monadic data structures. Okay, that's interesting. It's not really what I'm looking for, but I can't find the other one. So it says there's supposed to be a package called list transformers, and it should implement the list T, but can't find it. So sure. Yeah, it does mention explicitly this other library that I mentioned before, the list T one. So okay. The discussion of just talking about the identity. Okay, so exercise. Wonderful. I'm all about doing exercises. T and identity T are isomorphic for any type T. So one thing I noticed today on SodingStream that I really need to implement is just putting a little space underneath the bottom of my, right here, so that if I'm typing a long command, you can see the bottom of it. I just realized why he does that today. So it would be useful to have that, but I didn't do it today. I did create new overlays. So there's now a be right back overlay, and then just like a, hey, it's all me. So I made those today, or well, recently. So to identity is going to take an A and return identity A. Okay, and then we need identity. Oh, but it's not going to be here. I think it's in control monad. No, it's just in control functor, isn't it? Identity or something? Why is this failing? What do you mean? It says perhaps you meant. I don't remember exactly where it is, so let's go look. Did not clicked here. Identity. Data functor. I wrote control, didn't I? Yeah, sorry. Data. Gets me every time. All right, and then if we have an A, I mean, this is just going to be pure. And this one, we need to do this. This is a very easy exercise, but nonetheless. just says check that applying one after the other gives the same result. So let's just do that real quick. REPL. So if we write from identity to identity applied to 0 as an integer, because we should get 0. If we do the other way, to identity dot from identity with identity, probably need to import data functor identity and then do from I assume it has a print instance or a show instance, excuse me. So anyway, round trip, very easy to prove. I don't need that anymore. So that's fine. Done. Haskell's transformer library uses identity to remove the duplication of code between a monad and its transformer version. The trick is that the identity is nothing more than a transformer applied over identity. Yeah, we've seen these before. But one thing it says is for peace of mind, let us check that maybe T identity and maybe form the same monad. Trying to understand what it's doing here. Give me 1 second. So essentially what it's showing me is like it's plugging in maybe T and just pointing out that it's basically, it breaks down to a case at like, it breaks down to approximately the following. You know, case X of just X, FX, nothing, nothing. Something like this. If you apply the, if you start filling in the definition for bind, that's what's going to happen. Then it says prove or at least convince yourself that definitions of return and fmap also coincide. Okay, guess we can do that. It's an exercise, so sure. Oop, accidentally print something there. So exercise 11.4. Prove that maybe T and maybe form the same functor and all right, so if we take the following, return as the type A to maybe T, I guess is it IOA? I always forget the order of these things. The monad comes first, so MA. Something like this, right? So if we What is this doing? So this is going to be like maybe t return and if we fill in return, it's essentially going to be well, let's do it in steps. Right? And we're gonna have maybe t. Well, let's just actually let's write it this way because it's gonna be. And for clarity's sake, let's write this. Right, so we'll have an identity x I mean, how do I prove that these, oh, to prove that these are the same things, all I need to do is say 2 maybe t. I need to write a function that takes a maybe x and gives back maybe t identity x, or a, I guess I shouldn't write x here. 2 maybe t equals this, and then it should, wait, oh, okay. Let's also format this real quick because it's kind of ugly, and let's put this one back on the top. Right, so we need to prove that there's an isomorphism between these two types. So from maybe t is maybe t identity a to maybe a. So that's what we need to prove. So basically we can do case just x equals return x, and we need to enable a lambda case for this to work because we just do language lambda case. I'm starting to really like lambda case. If you're not familiar with it, it's like a pretty convenient way to write code, I think. So nothing, return nothing. There we go. So I can't return, I need to, this return, well, let's look at the difference between these two return functions. I suppose that will probably help. So this takes an a, right, and embeds it in a maybe t identity a, but I can't do that with a nothing. That just doesn't work. So first I need to embed nothing in an identity and then wrap, oops, wrong button. So this takes a maybe and embeds it in an identity maybe, and then I just wrap that with the maybe t constructor. So this is how the maybe t constructor works, data constructor. So I usually do this wrong the first time because I'm still getting used to the behavior of the wrapping and unwrapping of transformers. So it's like kind of tricky at first. So need to keep in mind maybe the data constructor or well, it's really maybe T, I guess, takes identity maybe A, right? So we're sort of unwrapping this inner maybe A, and that's how our monad T or our maybe T works. Something like this. All right, so in this case, and I can't use a do here. I've never once tried to match on this kind of function, but I guess no, we can't use bind because we need to. I think we're gonna write the following. Maybe T. Can we do this? And what's the type of this? Yeah. Okay, so again, we're kind of using what we just used here to unwrap this. And then that way, what I can do is I can actually use the function I wrote earlier from identity to get back. Oop, that's not what I want to do. So I can get back a maybe A here, and I don't have to do anything different. So let's see here. Can I write this in a different way that's more interesting? I don't, or not more interesting. That's probably a very wrong way to say that. But is there a way to write this in point-free notation that isn't terrible? Because you have to deconstruct this maybe T, otherwise this won't work. I think this is probably the correct way. We could also just pattern match this out, right? We could just say identity oh, except I need another parenthesis. Actually, what we'll do is we'll start keeping both cases. Do this. From so, and then we're gonna comment both of these, and we're gonna write from maybe T equals. So we first need to it's gonna be like run identity, run maybe T, I think. Yeah, and so that's the sort of just use the what are these called? The records, the transformer records. Not sure what the right term is for these. But they're the piece that basically unravels them. So you first unravel the run maybe, and then you just unravel the identity, and you have what you need. Also in point-free notation. So that's what I was thinking about. I'm already starting to have this like epiphany about how these things become unwrapped. It's coming slowly, but it's happening, and I think we're gonna probably use it a bit more here in a second. All right, so this time we're gonna talk about fmap, which is going to take, as we know, an AB, a maybe T M A, and return a maybe T M B. And this needs to be a monad, and M is going to be identity. So if we write a solution, which is going to be basically oh, we probably can't use that notation here. Let's just go grab it. Let's go make sure we grab the right one. Maybe T. Maybe. And functor. No. Okay. We're gonna say case run maybe T MA or whatever. MA is gonna have the type maybe TMA. Yeah, I shouldn't do 4. By the way, I'm just replacing, or I'm just writing the sort of solution to this. It's basically just a case statement. And then what we'll do is, I guess we need to just, I mean, we've already written that there's an isomorphism between these two things, right? So if I just replace this with maybe, doesn't that just mean that I can do this? Like, I don't even need to do any more work, I don't think. I think strictly by proving that these two things are isomorphic, I can replace A to B, maybe T M A with maybe A, and then maybe T M B with maybe B. Maybe I don't need to do any more work. So prove is isomorphic with maybe. In other words, I guess. Not sure if that's entirely correct, but like what they're looking for here, but I think that if you prove that, then those two, like the return definition or the fmap definition, can just strictly be replaced with the other ones, and the only thing that changes with their solutions is like an additional run identity or something. So I think I'm going to use this as my proof, if you will. As a final note, not only do we have an identity monad, but we also define, well, an identity T transformer. This transformer almost serves no practical purpose, unlike the identity monad. It goes very well, though, with the theme of things that compose and have an identity element that underlies many of the abstractions in Haskell. Section 17.4, which I suppose we'll get to in a while. It's going to be a little while, but it explains the role of identity T from a theoretical point of view. Okay. So since the combination of a transformer and a monad gives you back another monad, nothing stops you from applying yet another transformer to the result. For example, you may have a computation that obtains data for a person that needs access to a global environment, like a pool of database connections, that produces some logging and that also may fail. This computation can be assigned a type like the following. So first we're going to say data. Well, let's do the following. Yeah, I mean, we can just write data, not data, type message equals string, and type person equals string. I just want to make the following compile. So I think what you do when you work with these is you just write like a type that gives you your state, or a type that represents your monad stack, and then you just work with it. I'm not sure if people put this in a new type or not, but probably they do. So I would guess. So we're gonna have a new type called, I don't know, our stack. So we're gonna have a reader T of an environment. Hang on. We also need environment. Environment. Writer T. Here. Writer. Okay. So all I wanted to do is make this compile so that I have type checking later. I'm not too concerned with the actual types of these things. I think maybe a message in this case would make sense to model as text. A person would obviously be another data type, and then environment would also be a more interesting data type. But we'll just alias them to string for now. We call such a type a monadic stack. We say that maybe is the bottom layer and reader T is the top layer. We can expand the definition of each transformer to obtain the actual type under the hood. Wait, did I miss something? Oh, it says we could also write this in terms. Sorry, I missed one thing. So we're gonna change this inner maybe to maybe T identity for sort of making it a little more tricky. So yeah, maybe is at the bottom and reader T is at the top. I guess. So is we can expand the definition. So if we ran basically run reader dot run stack, that would have the type environment to writer t message maybe but where does the maybe t go? I think they're just pointing out that like this and the maybe are equivalent, so you don't need to worry about it, because you can't, wouldn't you need to run maybe t first? Well, I guess we can try it, right? I can just play with this type now that I have it. I don't need to actually make one. So if we write stack REPL, and then do type run stack, and then if we run reader t, import control monad trans reader. Okay. Yeah, so as expected, it's not unwrapping this inner monad, right? We're getting a stack 2, which is exactly what we want. So this is the reader unwrapping. And then we would unwrap the writer, and that would give us back environment to the message with this person. So it'll be a tuple of person, comma, message. Let's see if that's right. So run writer d dot. Of course. Oh, right. So I need to basically just make a type alias so that this will work. I think. Because run writer takes a writer. And the third thing is a writer. Okay, so let's do the following. We'll run this, and we'll write type equals I don't know. course that doesn't work. Oh, and then also this is starting to go off the thing. I was talking about this earlier, but let me just move this manually for now. So we need type. Actually, I got a better idea. Let's just try and write it in. Lumi would be so mad at me right now. We'll just write like this stack here. Wait, how do I get the writer T out of it? Oh, we're saying that these are equivalent. We're not actually unwrapping these things. I see. I'm misunderstanding this. Hang on. Reader T. Oop. Not what I wanted to do. That can be equivalent, I guess. Ah. Environment to, if we ran writer on this one, we should get, well, let's put the maybe T back in here. Although this is fine. It'll be maybe person message, I believe. Yep. And then it says not equivalent to reader environment writer message maybe person. So why are these not equivalent? Oh, because this is actually returning a writer. Although, and this is apparently not, even though it looks like it is. This is a little confusing to me, but my intuition for this stuff is not very good right now. It says, oh, okay. Hang on. So this is like, I get it. It's like environment to maybe person message. Because this is embedded. Okay. Let's not write this. The final All right, I like that a little bit better. Okay, so looking at the expanded type helps us understand the relation between the different layers of the stack. This specific combination needs an environment to start producing a return value. However, we only get back the execution log if the result was successful, since list of message appears inside the maybe here. So they're talking about this one. This is not usually what we want. We would generally prefer to get back a log, even more if the execution fails. So like this is probably more likely what you're looking for. A monadic stack that enables this functionality can be achieved by swapping the order of the bottom two layers. Which is exactly what I wrote there. Excuse me. This example shows us that we have to be careful when putting together big stacks. As we already know, the composition of monads is not commutative. Always want to put an extra syllable in there for whatever reason. So the order matters. Furthermore, it is difficult to understand only from the type expressed as a combination of transformers, which layers can interact with one another. In general, bottom layers cannot access values from upper layers, but the effects of those upper layers may still influence the execution of the bottom layer. All right, that's interesting. Okay, so I think now we're going to actually stack some transformers. So we're going to first talk about the MTL style. So going back to the beginning of our discussion about monad transformers, consider the stack we designed for evaluating an arithmetic expression that might fail. Did I already write this? State. I used state here. They used reader. I thought we used state before. Mm-hmm. Um, we didn't design. I'm very confused about this because we didn't design this stack before, but whatever. What's their point? I'm trying to find the point so I can at least explain it. All right, so we had this gets here, and the only difference between the gets for a reader is that this would be read ask, I guess. But I suppose you could probably write asks look up v dot unassignment, and that would be fine as well. Suppose we could try it real quick. See if it works. But I think everything else looks the same. So let's just try it real quick. I'm gonna copy this, and we're gonna put it down here. And then we are going to write eval prime. And we are going to replace state with reader and gets with asks. And oops, and this here. Okay, so it says oh, I see. But they don't wrap this in a maybe T. They put it in a do block. So I avoided that, I guess. So let's see if we can write it the way they do. So, I mean, I know that's going to work, but we already hinted at the solution. Sorry, I'm trying to read and figure out where we're going with this because I don't. Sometimes it's not immediately obvious why we're writing the code we're writing. And it's not like this is an exercise, so I'm a little confused. All right, so apparently monad reader, which gives us this ask function. Let's go check this out because maybe this is what's going on or what's not obvious to me. If we get ask, but we want it for the MTL, not in transformers. So let's do this. Let's go look at. Okay, so in transformers, I don't think it depends on this monad reader thing. Yeah, it doesn't. So, okay, that's why I'm getting confused. So, monad reader is a little bit different in MTL than it is in transformer. That's kind of the point. So, I understand why this is confusing now. In transformers, which I pretty much have only been using transformers right now. I don't know why. I have, and with that reader T, you'd only need to implement the monad instance, I guess. All right. Okay, so it just says in order to make the operations work for a specific monadic stack, we have to write the instances. For each of these classes, we need two kinds of instances. You need those instances that really implement the operation. For example, a monadic stack that contains reader T is an instance of monad reader. If the top layer of your stack is not reader T, you need to pass through that layer and find a monad X below. For example, if maybe TM is a monad reader, that means M must be a monad reader. Since maybe T does not provide such functionality, we have to implement it, I guess. Okay. So it says, in general, this means that if we have n sorts of monads, we need to write n different classes of n instance. Yeah, this is the n squared problem people talk about, right? This gives us a grand total of n squared instances to write. Fortunately, it is not our task to write all of those instances. The MTL packages makes them available for Haskell. In chapter 12, we will look at techniques to prevent this sort of code duplication. Table 11.2, the table that shows you what instances are available, I guess. Okay. So then we get into automatic derivation for your own monadic stacks, which I guess is for MTL specifically. Although we're using transformers, so I don't know that this is going to work exactly. I suppose I could switch to an MTL version real quick. Do we get into transformers next? There was this package that I thought was really interesting called Ether in here. but it seems to be not maintained anymore. Excuse me. So this says basic concrete monads live in either the base or transformers package. The corresponding monad transformers live in the transformers library. For classes of monads, you can choose between MTL or ether. I don't understand the relationship between MTL and transformers then. Don't I get these things in transformers? I'm a little confused right now. So let's just do the following. Transformers. So we get ask for reader, writer state. What's the T in here? Sure. We get ask, we get asks. We probably have a get and a put because I've used them before. Does transformers just depend on MTL? Is that what's going on here? And I'm just missing the point? No, it only depends on these two things. Okay, so alternatively, it can be used with the non-portable monad classes in MTL or monads TF, which automatically lift operations introduced by monad transformers through other transformers. Interesting. Not entirely sure I understand. All right, well, let's try the following code and see if it works for transformers, I guess. Because I'm a little confused at what's going on here. So we need another generalized new type deriving. We'll write this. Applicative, alternative, monad, monad plus. That's in data applicative, right? Oops. Control applicative? right here. Get rid of this. Uh, it says Scala does not have a feature similar to new types, so developers use monad transformers directly. This prevents the problem. Is the problem just that these aren't automatically derived? Is that a problem? I guess. Can it like just start doing like arbitrary things? Oh, well. No instance for monad IO identity. Oh, yeah, I guess that makes sense. It would have to be. This would have to be IO for that to work, I suppose. All right, so we know quite a bit about lift IO, so I'm not too concerned about that. I'm still not super clear about like the entirety of the difference between MTL and transformers. Maybe at the time of writing this, the transformers library did not contain all that it contains now, or maybe I'm misunderstanding the point of MTL. Not 100% sure right now. Okay. So anyway, the definition of the monad reader type class has a declaration added to it, bar m2r. This annotation is called a functional dependency. The way to read it is that given a monad m, we also know the type of r. In other words, the type r is a function of type m. We don't have this, like, the transformers package doesn't have this, as far as I understand. I suppose we could just make sure via Hoogle. Reader. Okay. Anyway, the point is this little thing at the end here. So it's just saying that M implies R essentially. This additional element is necessary because when we write a function that is parametric over the reader, the monad in the result type is simply M. Excuse me. So it says, on the other hand, functional dependencies forbid us from declaring that a certain computation needs access to two pieces of the environment in an easy way. Let's just see this error, I suppose. I'm still very confused. I don't understand the point of this current section. Just telling it like it is. Well, I don't even have monad reader, so I don't even think I can test this. I think I'm just gonna continue. Yeah, I don't think this is entirely correct anymore. So that, I think that's why I'm having trouble. Anyway, so let's just move on. And this next section is talking about a parser. It says parsers for free, so that's what we're gonna do, I guess. So parsing for free. I'm hoping that as we go through the book, maybe this will become more clear. But I truthfully don't understand. I have like my nose is twitching. Really annoying. So I have 5 people watching right now, so I wanted to thank somebody for subscribing while I was off stream with Twitch Prime. I don't know how to pronounce your name, but it's like Sila something. So if you're around, like, please say hi. I really appreciate that you did that. Hoping that they show up eventually so that I can thank them in person. All right, so we need a parser type. So we're gonna have a parser of A that is a, what's up, Warren? I did see your message, by the way, in Discord. I just I haven't been able to think about it any more carefully, so you're gonna have to bear with me. Yeah, no worries. Oh, I wrote S for whatever. So, because I want to do this in a sort of the new type way, we're gonna do that. So it's gonna be new type parser. I don't know what to think about it right now. Is basically what it is. I don't know how to use it or like to find the right way to co-stream with you. So we'll figure that out at some point. I don't know what the right answer is yet. If that makes sense. That might be like a weird way to say that. But I mean, I'm trying to figure out how to do more community stuff, so I just need to figure out how to make that work. Because like the only thing I can think about doing is making an extension to what I already did with Jappy. But like, I think the point is that the person who would encounter our version, the Jappy and my version, would then continue on to Nick's pills. So, well, yeah, we would use Zoom, but like, what would we talk about? That's the thing I'm trying to figure out. Um, like, I think the key for me is like I should just mess around with that Nick's pills thing and then just start using it, right? Like, I don't need to. I'm not 100% sure if I need more description of what it is, right? I just need to start using it and see how it works for me, if that makes sense. All right, so this is interesting, isn't it? All right, so okay, let me I'm gonna keep this in mind. Don't let me forget about this. But I'm not really in the current, like, I don't have enough time to spend to start playing with Nix to even get there yet. And I kind of want to at least finish some projects. Like, I'm not too concerned about learning Nix right now. If that, like, if it was definitely a good, um, it was a good first example of teach me something, but I'm not ready to continue learning Nix at the moment. I have way too much on my plate at the moment. Okay, so we're gonna have a run parser. I guess list is a monad. Sometimes I forget this. This just needs to be a monad, and uh, that's just the list type. I can see how this looks awkward for like someone beginning, like in Elm, for example. This would just be a literal list. You wouldn't have to do anything. So anyway, there's like a poem that goes along with this. So it's a parser for things is a function from strings to lists of pairs of things and strings. Have a tongue twister. So you need to input a string, so that's this piece, and you need to output a list of A with string. So that's kind of the point. So it's like, think of, this is equivalent to state to, not state, string to list of string A. Or is that backwards? A string. Yeah, the other way. A string. But don't let me forget that, Oren. I will figure out a way to make that work. I don't know exactly how we would do it yet, if that makes sense. Because I want to turn it into like a general teaching thing. I don't want it to just be you guys teach me something and then, it's not useful for other people. So that's the thing I'm trying to figure out. Okay. So if you've ever tried to write the functor, applicative, monad, and monad plus instances for the parser data type above, you know that it is painful to get them right. But we never have to do it in the first place since they come for free if we formulate parsers using monad transformers. In order to build actual parsers, we need two primitive operations. The first one checks that the first character of an input string satisfies a given predicate and returns it if successful. Oh yeah. I agree with that. I can see how it's useful for many different things. I'm particularly interested to see if I could use it as a replacement for the modules system on the high performance computing cluster. I don't know if it will work, but so we need this function. So given a predicate, return a parser car. E equals state T I don't think that this will type check because I have it in a new type, but we'll figure out where we need to fix it here in a second. C CS. I didn't know you could do this. PC. Oh, I see. We're pattern matching on CCS. Wait, no, I don't think I knew you could do this. CCS. All right, so S. Let's do GHCID C stack rebel. I'd like to see the full error. Just all good, huh? There you go. Right, we need to wrap it in a parser. So it's really parser dot state T. Think. Yep, and then we can do just case. There we go. Yeah, so when you have something like lambda s to case s of, that's like the lambda case thing. So just, if you have HLint, it will always tell you that. You don't have to really deal with it. I'm not sure I realized that you could write something like this. I don't know that I've ever written anything like this. I would have written the following, basically. Um, I find that a little tricky to read, even myself. Mainly because I've just never, I don't know that I've written it before, that's all. I would have written this probably. If PC, then CCS, else empty. And apparently we can use a list comprehension here, which is kind of interesting. Oh yeah, that looks great, actually. That's actually fantastic. I would have never thought about this, right? Because all that you need over here is a predicate. So if this is true, then, or I'm sorry, all you need over here is a Boolean. So if this is true, then it will just print this. Otherwise, it'll give you an empty list. That's actually an awesome piece of code right there. Thank you. HLint is like my favorite piece of software, I think. It basically was like, yeah, you should use lambda case. Yeah, you can fix this code to use a list comprehension. That's awesome. Okay, anyway, that's pretty cool. So if we get an empty list here, that indicates failure basically. And if we get anything else, we get that's like positive. Okay, so, and we need this function, character car to parser. You only need 2 functions to write a parser. Pretty wild. So it's just satisfies dot if you want, you can also just write this. Sorry, I'm starting to recognize these things. Right, you can write this, but you really don't even need to. You can write the following: point free syntax for life. Right. Apply this to a car, you get equals equals the thing, and then satisfies of that, which is your predicate. Okay. Actually, we can also take car as the primitive function. Write car directly in terms of state t, then use car and the guard function to define satisfies. All right, so we're gonna exercise. I love exercises. Ifs off. Oh, did you know we have ifs off? Damn. He's actually behind me. Can you see him? He's hard to see, probably. There's Hodor. Damn. I need to find like an artist to make me some emotes that involve Hodor, because the golden squirrel is definitely my favorite part of. I don't know where I found that, but I think it's just really funny. Shirts, yeah. I don't know that anyone would buy shirts to start, but I mean, because my viewer base is pretty small. But if we could write like a really funny meme with piffs off, I mean, there were people who were tweeting about it who I wouldn't have expected to tweet about it. So some people like it. I think it's hilarious. All right. Okay, so let's try this. It's here. So we're gonna need like parser dot state t case. Hmm. Oh, this is just gonna fail, right? Um, what am I supposed to do here? I need to have a car and a string. Yeah, I know that, but I want to know what this is. This is a string, right? So we are going to, given a string, oops. Okay, so given an empty string, we do still want to turn an empty list. And given a C, oh, we're just doing the same thing. It's literally the same code. Sort of. Except we need to use like X, XS. And then we'll say X, XS, X equals C. Yeah, so that's right. And then we're gonna write satisfies write car directly in terms. All right, that's the key here is we can't take a character. I don't think. Write car directly in terms of state T. Hmm. Given a string, what I'm trying to figure out is how do I emulate this satisfies thing? if I just have a character that equals C. Oh, maybe I just use like a let. I'm not 100% sure. Let's see. I think I need this back though, because I don't see how else I write this. C. Then we want to write satisfies prime parser car satisfies equals B. Oop, missed a prime. Okay, so let's put this up here. How do we use car? So what we need to do is get the state, I guess. So we would do like C get no idea what that means. Monad state is not a unary constraint as expected by deriving clause. I don't know what monad state is at all, so state. There's literally nothing called monad state. Whoops. What? What's the error? There we go. That's what I wanted. I don't actually need to derive any of this stuff. I don't even know what that error like meant, to be completely honest. Right, so this is just the The parser. Was this just supposed to be C? I don't know if this is actually correct, but it does say then use car and guard. I guess I'm not using car here. Not exactly sure what I'm supposed to do here. This is completely ignoring the car function. This is basically just the monadic version of this in the state T monad. What if we write all right. So I think here what we're gonna do is do the following. So if we have C and CS, we use, I guess, car C, car prime. And then we probably do something like run state T, but it's not run state, it's I think it's eval. What is it? Let's just look for state T in here. I think we want the lazy one. Hmm. Not really sure what I'm supposed to do here. I use car and the guard function to define satisfy. What am I guarding? I don't understand what I'm supposed to do here. I'm a little stuck. Unless this is just wrong. Let's come back to this. I don't feel like struggling on this right now. Too tired for that. I don't understand what I'm gonna do here. So if I have a parser of car, is there like a function in here that takes like I certainly don't want to mess with the types, and that's not really the shape of my function. Can get the current value. I'm not sure what I'm doing here. A little confused. It's okay. Let's just keep moving on, because I'd like to finish this chapter and think about something else tonight before we go. All right, so if we get an end, that's basically like you should end up with an empty list, and that's going to return unit and this. Otherwise just return an empty list. That's failure. So this is like a function that checks for the end. It's not yeah, okay. All right, so we can write the following. Apparently. Hex digit, hex digit, hex digit. Where? digit equals satisfies column A, B, C, D, E, F. B, C, D, E, F. 0, 4, 5, 6, 9. Okay, so we need to derive. We did need to derive these, otherwise this wouldn't work. Alternative. Redundant bracket, sure. Wait, oh, bracket. What bracket? I just realized what it. Redundant bracket. What does that mean? What did it just remove? Oh, these. Sorry, I got confused at where that was telling me to remove this. Okay, so this is a little tricky, for sure. Pretty beast of a function right here. But like, I mean, I recognize it because we've done parsers before. But basically, this hex digit is just a parser of character that's just checking that our value satisfies that it's in these elements. And so we're building up a partially applied function in this first bit here. So this is basically building the partially applied function, and then that way we can just use applicative to apply them to 4 digits currently. All right, I mean, that's kind of cool. I didn't realize it was that easy to write a parser. Like, that's basically... Well, I mean, there's a lot of stuff going on under the hood over here, but... or not there, sorry. Here. But, you know, it's pretty powerful. Cool. So I want to switch topics for a little bit because I'm sort of interested in something, and yeah, so we're gonna do that real quick. Well, let's commit this code first. Should only have changes to that, so